All right, kids. This is kind of a sad moment for me because this is the beginning of the final chapter that I'm going to go over for the Stats with Glenn video series. So this is chapter 12. There is another chapter in the book, chapter 13. After having taught this class a million times, I found that I never get around to actually getting to chapter 13. You can read it on your own. It is on a topic called chi-square, and it deals with the situation of having two categorical variables or non-continuous variables. Final chapter that we're going to go over here for the video series, chapter 12, analysis of variance, or what the cool kids call Anova. Isn't that a cool sounding stat right there? Anova stands for analysis of variance. As is true with t-tests, there are lots of different kinds of ANOVAs. Remember with t-tests, we talked about a situation where you're comparing scores on one variable from the same participants with scores on another variable. There's an ANOVA like that. We call that the repeated measures ANOVA. You remember with t-tests, we talked about the between groups t-test where we wanted to see if data from one sample representing one population are significantly different from data in the second sample representing a second population. There's an ANOVA for that. That is called the between groups ANOVA or the one-way ANOVA. There are also more complex forms of ANOVA. You can do an ANOVA with what's called multiple independent variables. You could do an ANOVA, for instance, to see if students who use the textbook versus who don't use the textbook, and students who go to a private college versus a state university differ from each other in terms of how they do on a stats exam, as an example. So you have two independent variables, state versus private university, textbook versus no textbook, one dependent variable of scores on the outcome measure. There are several other kinds of ANOVA as well. So when you go into a PhD program and when you learn more advanced statistics, you will learn about the more advanced forms of ANOVA. The guts or the basics of the ANOVA are found in what we call the between groups ANOVA, or sometimes it is called the one-way. In the one-way ANOVA, you have two variables. You have a categorical variable, usually with 3 or more levels. And then B, you have a continuous variable, or what is called a continuous dependent variable. DV standing for dependent variable, and dependent variable simply means your outcome variable. So you remember in the prior chapter for between groups t-test, we had a categorical variable, whether people got an experimental version of a drug or a placebo version of a drug. And then we had a continuous variable, which was their temperature 3 days after having taken whatever drug they were on. A one-way ANOVA is an extension. It is a natural extension of the between groups t-test. The only difference is that with a between groups t-test, you have 2 levels of your categorical variable. And with your one-way ANOVA, you technically can have 2 levels, but you essentially usually have more than 2 levels. So you can have 3 levels or 4 levels or 5 different levels and so forth. So, and it's called the analysis of variance, and I'll tell you why. I'll explain a little bit why. The analysis of variance leads to something we call the F ratio. The F ratio of the F statistic. The F statistic equals MSB divided by MSW. We're going to start with that, and we're going to sort of step back and then move toward calculating that. But let's start so we can understand this conceptually. Let's start with this. That F equals MSB divided by MSW. MSB stands for mean square between groups, but think about it this way. It is an index of how much variability there is between groups or between means of groups. So how much do the means of groups vary from each other? So this is between group variability. And MSW stands for, nothing happened, kids. Everything's fine. MSW stands for mean square within groups, or it is an index of within group variability. Okay, the example that I use in the textbook, and I like it so much I think I'm going to summarize it here. We can think of this as what's called a signal detection task, or a signal detection process. The F ratio is looking at a whole bunch of scores. Scores that are from different groups. And it's looking at the means of those different groups. And it's asking the question of whether the means from the different groups are different enough from each other that we can say that they are different, not because there's just within group variability within each of the groups, but because there's actually something substantially different about the different groups. So it is a signal detection task. I think about it as a biologist in the jungle in Africa. And if you're a biologist in the jungle, you hear a lot of different noises. And let's say that there's some bird that you had learned you thought was extinct, but it might still exist. And to detect whether the bird exists, you're using all kinds of fancy acoustic equipment. So you bring your acoustic equipment into the jungle of Africa, and you hear all kinds of background noises. There's all kinds of other birds, there's all kinds of other animals. There's all kinds of background noises in the jungle of Africa. But then suddenly you think you hear the call of this bird that you thought was extinct. You're not positive, but you think you hear it. So you fiddle around with your device and you try to turn down the background noise and you try to pick up whatever frequency is associated with that rare bird that might have been extinct. So you're trying to detect a signal against a sea of noise. That's essentially what you're doing with your analysis of variance. That's essentially what your F-test is doing. You're trying to detect whether there's some kind of signal, some kind of effect, a between group effect, against a sea of what we call within group variability. And as you see how we calculate it, just keep that metaphor in mind and you'll find it useful. And this thing's probably not going to fall again. Just going to put that out there. Can't promise. Austere conditions, kids. State University. Fun SUNY now, this is why. Okay, so here's an example that we're going to go with. In my house, we have dogs. And in fact, you might have noticed from some of the prior videos, Nico and Cujo love to bark. And when Ed next door turns on the motorcycle, man, do my dogs love to bark. But I love them anyway, and we've had them for a very long time. So think about dogs quite a bit. And the joke in our house, which not everyone thinks is funny, is that Nico is not quite as intelligent as Cujo. Whether it's true or not, we're not sure. My wife does claim that she gave the two of them an intelligence test one time designed for dogs, and that Nico apparently failed. But it's kind of a discussion for another topic. But that got me thinking of an example which has to do with the intelligence of different dog breeds. I happen to personally know Stanley Coren, who's probably the world's best known dog psychology expert. I met him at a conference and he actually convinced me to get Nico. Years later, I feel like I should talk to him about that decision. But in any case, Stanley Coren is famous for studying dogs from different breeds and essentially saying how intelligent dog breeds are relative to each other. And he's famous for showing that border collies are, based on his criteria, the most intelligent of the dog breeds. So we're going to use this example, this general concept, to address the analysis of variance. Do 3 dog breeds differ in terms of IQ, or what I'll call doggy IQ? So this is a classic Stanley Coren kind of question. If you're interested in his work, he actually has published over 30 books on dog psychology, and he does publish a blog on dog psychology for Psychology Today, which actually is, every time I read his stuff, I'm fascinated by what he has to say, so you might be interested. Stanley Coren, I'll just put his name up there for you, in case you're interested. So Stanley Coren is the guy that I'm kind of basing this example on. So do 3 different dog breeds differ in terms of doggy IQ? So let's come up with some numbers. Here we have Border Collies. Famously intelligent Border Collies were bred in the northern part of England, the southern part of Scotland, right on the border. They herd sheep all day, and a typical Border Collie will run about 100 miles a day herding sheep, and they are absolutely essential for the sheep farmers in different parts of the world, but especially in that part of the United Kingdom. Border Collies are famous for being really smart. I'm going to put labs up here. Labs are famous for being nice. They're nice, they're bouncy, they're not dumb necessarily, but you know, they're kind of not Border Collies. And here, by popular demand, I'm going to put Chihuahuas. If you're offended by any of these examples, I suggest you contact our associate producer by email, and we can go from there. So I'm going to put the data. IQ tests generally are on a scale with about 100 as a mean and a standard deviation of 16. This is how human intelligence tests tend to be designed. So I'll put numbers that are kind of similar. I'm going to give you data from 3 Border Collies. I'm going to give you a 120, a 100, and I'm going to give you a 130. Okay, so there's our Border Collies. For the labs, we're going to put this as 100, and the next one's going to get a 90. I'm going with small n's. I'm going with unequal n's, just like I did in the example with between groups t-test, just to get you to realize that the analysis of variance, the way that it's computed, deals absolutely fine with unequal n's. It's designed to be able to deal with unequal n's. So if you're doing a research project, you have 3 different groups, you don't have to kill yourself to make sure you have the same number of participants in each of those 3 groups. The analysis of variance doesn't care. Finally, we're going to go with our Chihuahuas over here. We got a 60, and we have an 80, and I'll throw in another 80 right there. Okay, so there's our Chihuahuas. I hope I have enough space to work this out, but we'll have to figure it out. One thing I think I'm going to do, actually, I'm going to write down Yeah. So, yeah, Dana, if you write down those numbers, that's great, and then we can come back to it. Okay, so let's take a look at the analysis of variance. And again, for the Border Collies, we have 120, 100, and 130. For the labs, we have 190. For the Chihuahuas, we have 60, 80, and 80. I can erase that, Dana?
Yeah.
Okay, thank you. Okay, so we'll do the border collies first. While we're doing this, over here on the right, I'm going to put how we're going to get the F. F equals MSB divided by MSW. Remember, that means it's an index of variability between groups, between means of groups, relative to the amount of variability caused by within-group variability. It's just the fact that there is variability within each of the three groups. MSB equals SSB divided by NG. Okay, NG simply means the number of groups. Okay, so I'm going to do this in a way that kind of gives us our F ratio at the bottom. I'm dissecting it all the way up. I hope I have enough space. I think I should. So F equals MSB divided by MSW. Here's what MSB is. MSW equals SSW divided by DFW. I'm just checking one thing, kid. I want to make sure I get this 100% right. Yeah, actually, you know what? MSB, sorry about this, I thought I might have done this. MSB equals SSB divided by DFB, not NG. Sorry about that. This is correct. SSB equals SSB1 plus SSB2 plus dot, dot, dot. Okay, so at some point we're going to come up with how we figure out SSB. It's not a very complicated process, and we're going to do whatever that process is for the number of groups we have, which in this case will be 3 groups. SSW equals SSW1 plus SSW2 plus dot, dot, dot. So SS, if you recall earlier, means the sum of the square deviation scores. It's an index of variability, and the way Anova is computed, it is the index of variability that's used for these particular calculations. And I'll put up 2 degrees of freedom terms because they're going to be used down here. DFW equals DF1 plus DF2 plus dot, dot, dot. Degrees of freedom within. You'll see this stuff, I'm just going to put these formulas up here, digest it, and you'll see that it's all, every step is easy to compute. There's a lot of calculations, but every step makes sense and is easy to compute. Finally, DFB equals NG minus 1. So that's where my NG, remember before I messed it up, I put it here accidentally. Degrees of freedom between is the number of groups minus 1. We have 3 groups, 3 minus 1 is 2. So in this particular case, DFB equals 2. Those are all the formulas that are going to feed into F. Okay, so we're going to do the steps in hypothesis testing. Now, for hypothesis testing with the analysis of variance, or the Anova, this is the only time where we're going to start with the null hypothesis and not with the research hypothesis. The null hypothesis is that the population means are all equal to each other. That's always the null hypothesis with an analysis of variance. It's always that the population means are equal to each other. And usually students like this. The research hypothesis is what I like to call not H sub 0. And I like to put a little exclamation point there. Not H sub 0. Anything except for H sub 0 will reject our null hypothesis. If we have evidence that mu1 is greater than mu2, we'll reject the null hypothesis. If we have evidence that mu1 is less than mu3, we'll reject the null hypothesis, and so forth. On the one hand, it makes articulating the research and the null hypothesis easy, but on the other hand, it's also a liability and a limitation of the analysis of variance. As you'll see when we finally get around to going through the entire problem, the information that you can extrapolate from your Anova is very limited compared to what it is for other statistics, and there's ways that we deal with that limited nature. But there's your research and your null hypothesis. Step number 2, your comparison distribution. Okay, comparison distribution. See if I can fit this whole thing down here and possibly leave it the whole time. I don't know if I'll be able to do that. But the comparison distribution is an F distribution that looks about like this. On the y-axis we have probability. Okay, so the F distribution is a probability distribution, as is true for all the hypothesis testing distributions that are comparison distributions. The x-axis is different F ratios. Now, interestingly, at about 1.0, that's the peak. So the most common, if your null hypothesis is completely accurate, if there's no evidence against your null hypothesis, the most common F that you will find is 1.0. Take a look how F is computed, MSB divided by MSW. If F equals 1.0, that means that your between group variability estimate equals your within group variability estimate. That means that your between group variability, or your signal, is nothing more than you would expect based on your within group variability estimate. So if you have nothing, essentially, your F will be 1.0. F can be below 1.0. That usually just means you really also have nothing. F is interesting because it's a positive number only, because it's a ratio of 2 variance estimates, so it's a positive number only, and your tail will be out to the right. So you're only going to have a significant F on one tail. There's no such thing as a two-tailed F ratio or F test. So our comparison distribution is an F ratio. However, it is also a specific F ratio. It is an F ratio based on degrees of freedom between and based on degrees of freedom within. Now, degrees of freedom between, that corresponds to the number of groups minus 1. We have 3 groups minus 1. 3 minus 1 is 2. Okay, so that's pretty easy. Degrees of freedom within. Each group has a certain N. Okay, so remember, border collies, N1 equals 3. For labs, I think I had 2. So N2 equals 2. And for chihuahuas, N3 equals 3. Okay, so if you recall when I put up the data at the beginning, I have 3 border collies, I have 2 labs, and I have 3 chihuahuas. Now, degrees of freedom within 1 equals n1 minus 1 equals 3 minus 1 equals 2. Okay, so degrees of freedom within for sample 1 is 2. Degrees of freedom within 2 equals 2 minus 1, which is 1. And degrees of freedom within 3 equals 3 minus 1, which is 2. Okay, simple math. There's 3 groups. Each degrees of freedom within is just the number in each group minus 1. So it's 2 and 1 and 2. And degrees of freedom within is degrees of freedom within 1 plus degrees of freedom within 2, etc. So it is the sum of these little degrees of freedoms, which equals 2 plus 1 plus 2, which equals 5. So for this particular example, degrees of freedom between is 2, and degrees of freedom within is 5. So let me show you what I do with my comparison distribution. When I write my F distribution, or when I draw it, I demarcate this information. I write dfb equals 2, and I write dfw equals 5. I do that because there is a different mathematical function for every analysis of variance or every F distribution, depending on the degrees of freedom between and the degrees of freedom within. So let's take a look at our F distribution, which starts on page 331. I didn't give you alpha, but let's say that alpha equals 0.05. We're going to start with our standard alpha. Okay. So the degrees of freedom within is represented here. And the degrees of freedom between is the numerator degrees of freedom is represented here. Okay, so for the within degrees of freedom, we have 5. So I'm going to go to here. Significance level, I can pick alpha equals 0.01 or 0.05 or 0.10. We're picking an alpha of 0.05. We're starting with that. And then the number of between group degrees of freedom, also known as the numerator degrees of freedom, it's the top part of that ratio, is 2. And so we have a single number, which is 5.79. 5.79 means we have 5 within group degrees of freedom, 2 between group degrees of freedom, and we're going with an alpha of 0.05. So that is where that 5.79 comes from. So you base your F critical actually on that. So step number 3 is F critical, which is what we just looked up, which is 5.79. And I'll demarcate it over here. And that critical value is a function of the degrees of freedom between and within. So every F distribution is different depending on the number of between group degrees of freedom and the number of within group degrees of freedom. This particular F distribution is such that with an alpha of 0.05, the F critical is 5.79. But that will change with different degrees of freedom between and different degrees of freedom within. So now we've actually got 3 steps. The research and null hypothesis, the comparison distribution is this F distribution, our F critical value is 5.79 over here. So now we need to compute F, or what we call F obtained. And you remember that F obtained equals MSB divided by MSW. Okay, you're going to see, while there's going to be a good bit of calculations, everything that we're about to do should make sense. And it's going to feed into these smaller equations over here. Okay, so the first thing we're going to do is we're going to deal with the border collies. Okay, so we can call them X1. M1 is the mean for the border collies. Which is 116.67. Okay, so now we have X1 minus M1, the deviation score. Okay, so when we get SSW sub 1, the sum of the square deviation scores within for group 1, that's going to be exactly like what we've been doing with the sum of the square deviation scores all semester long. So let's take a look here. We have 120 minus 116.67, which is 3.33. 100 minus 116.67, which is negative 16.67, I think.
Yeah.
And then 130 minus 116.67 is 13, yeah, that adds up, 13.33. Okay, so those are our deviation scores. Next we're going to get our square deviation scores, which is, again, just like we've been doing all semester long, we're just going to square those numbers. 3.33 times 3.33 is 11.09. Uh, 16.67 times 16.67 277.89. It's a whopper. And then finally 13.33 times 13.33 is 177.69. Okay, so those are our square deviation scores. SSW1 means the sum of the squared deviation scores within for group 1. So it is simply the sum of that column, just like we've been doing all semester long. 11.09 plus 277.84 plus 177.69 equals 466.62. Okay. So looking over here, how we're ultimately going to compute F, SSW equals the sum of the little SSWs, SSW1, SSW2, and so forth. So there's SSW1. That's one of the pieces of the puzzle. Now, I'm just going to hold that over here, actually. SSW1 equals 466.62. And the other thing I need to say, you know what? I'm going to try and save everything. Let me try to erase down here. The F is pretty important. Okay. So now we're going to do the same process, but for the labs. Okay, so they're x2. And Dana, can you remind me the lab data?
Yeah, it is 190.
190. Okay, so you remember we had only 2 dogs in the lab category. Okay, and what we're working toward right now, we have SSW1, we need SSW2. Okay, so that just means the amount of within group variability for the labs. The mean here is 95. X2 minus M2 is 5 and negative 5. X2 minus M2 squared is 25 and 25. And SSW2 is 50. Okay, so do you see that? It's just the sum of that column for the labs. So SSW2 equals 50. And finally, for group number 3, we have the Chihuahuas.
60, 80, and 80.
Thank you. Okay, so we had 60, 80, and a third one was 80. Okay, let's see if I can, Chihuahuas are small, maybe I can squeeze the space right here. Okay, so M3. Um, 16. So that's 220 divided by 3. The mean there is 73.33.
Yeah.
Is that what you got? Okay, x3 minus m3. Negative 13.33. This looks like 6.67. And this looks like 6.67. Does that check out about right, Dana?
No, yeah. Sorry, I was looking at the wrong one.
Okay. And then next I'm going to square these. X3 minus M3 square. Okay, so 13.33 times 13.33 equals 177.69. 6.67 times 6.67, 44.49. And this 6.7 squared is also going to be 44.49. And then SSW3 is going to be the sum of that column, which is 177.69 plus 44.49 plus 44.49, which is 266.67. So SSW3 equals 266.67. Okay, those are all indicators of how much within group variability there is. Remember, the F ratio is ultimately how much between group variability there is relative to how much within group variability there is. Those are all estimates of within group variability within each of those 3 samples. Okay, SSW equals the sum of all of those together. Okay, so SSW equals SSW1 plus SSW2 plus what I call dot dot dot. Meaning, in this case it's SSW3, but if there was 4 groups or 5 groups, you could imagine more. But SSW is the sum of all that, so that's 466.62 plus 50 plus 266.67, which equals 783.29. Okay, so big SSW is the sum of the little SSWs, which is 783.29. Now, if we take a look, we can jump ahead a little bit. MSW, and you remember that is actually half of the F ratio. MSW equals big SSW divided by DFW. So MSW, we can compute right now, is SSW, which is 783.29, divided by DFW, which we prior concluded was 5. So 783.29 divided by 5 equals 156.66. Okay, that's a magic number right there. We don't want to lose that one. 156.66. That is MSW. That is half of our F ratio equation. Again, 156.66. Got that one?
Yeah.
Got it. No, thank you, Dan. Okay. So we're kind of halfway there. Our analysis of variance, our F ratio, is looking at the amount of between group variability relative to the amount of within group variability. We now have our appropriately weighted index of within group variability, MSW, which is 156.66. Next, we need to figure out MSB. And we're going to go through the whole process to figure out MSB. To figure out MSB, I'm actually going to erase a bunch of stuff. Let's remember that F critical equals 5.79. And let's see if I can do it with this space. By the way, when you're doing an analysis of variance problem at home, give yourself a lot of space. Give yourself as much space as you can. When you're doing the homework problems, when you're going through the problems in the textbook, you'll see that there's a huge benefit to giving yourself a lot of space. Because we actually, for the amount of space that we used, because we're looking at both MSW and MSB, we essentially need twice as much space, which is actually why I have the whiteboard as landscape instead of portrait today, just for that particular issue. Okay, now the next thing that we need to do is for each raw score within each group, we'll start with the border collies, we need to take a look at the mean. And we're going to compare the mean with something we're going to call the grand mean. The grand mean, or G sub m, simply equals the sum of all the x's divided by the total n. It is the sum of every single score across groups. So the grand mean doesn't care what kind of dog you are. The grand mean is across groups. There's 6, 7, 8. There's 8 total dogs in this study. So it's going to be all those scores added up divided by 8. So that is 120 plus 100 plus 130 Dana, do you happen to have that?
Yeah, 690.
The answer is 690. I referred to Dana because I feel like I totally messed it up. Okay, so the sum is 690. Okay, divided by.
Oh no, that's the, sorry, that's the total.
That was the sum of x.
Yeah, hold on.
Divided by n, which is 8.
No, that was the grand mean. That was everything.
Well, that was the sum of everything. But the grand mean is the sum of everything divided by n.
Yeah, but I already had that divided. 690 was already divided.
Oh,
Wait, maybe not.
I don't think so. Let me.
Okay, hold on. Maybe I just messed it up.
That's okay. Let me try it again. So 120 plus 100 plus 130 plus 100 plus 90 plus 60 plus 80 plus 80. I got 760.
Yeah, me too.
Okay.
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 I don't know where that came from.
That's okay. It's all good, kids. 760. We have confirmation. So we add up all those scores. That's 760. We're going to divide that by 8, which is the total number of scores, and we get 95. Okay, let's not lose sight of what that means. That means that across all the 8 dogs being studied, the average doggy IQ is 95. Now, what we need to do for every calculation we did before, for Border Collies we did 3 calculations, 1 for each score. For Labs we did 2, for Chihuahuas we did 3. We need to do that same thing, that same number of times, except now we're comparing the mean of the group with the grand mean. So the mean of the group for Border Collies is 116.67. I'm actually going to write that 3 times to give ourselves the visual understanding that we're doing that same process we did before. We're going to do that the same number of times, and that's a way of putting the MSB and the MSW on the same scale. So that's why we're doing that. So we're going to do this 3 times. We're going to subtract out the grand mean. We're going to do this 3 times, 95. And then we're going to get the deviation score. And then we're going to get the square deviation score. Okay, so you'll see this. Once we get one answer, we're going to have the correct answer. So 116.67 minus 95. Okay, so that equals 21.67. I can write that 3 times now. And 21.67 squared equals 469.59. I can do that 3 times. 469.59, 469.59. And now SSB1. So SSB1 is the sum of that column. Sum of the squared deviation scores between group for sample 1 is what that means. So it's 469.59 essentially times 3, which equals 1,408.77. Okay, I'm gonna circle that. That's an important number. That's SSB1. That's gonna go into big SSB, which will go into MSB, which will go into our F ratio. So we're holding on to SSB1. Let's figure out the same thing for SSB2. I'm gonna make a little wall right here. Okay, we have M sub 2 is 95. It looks like just by chance, the average lab IQ is the same as the grand mean of 95. So that's kind of interesting. And we only had 2 labs, so 95 minus 95, and then M2 minus GM The deviation scores are both 0. And then we can square that. M2 minus GM squared is 0 and 0. And SSB2 equals 0. I'm going to circle that. So the sum of the squared deviation scores between for the lab group is 0. That is conceptually meaningful. That means that the average for labs of 95 is the same as the grand mean, which is a way of saying that labs are absolutely average in terms of intelligence. Not sure if that's true or not, but that's what that would mean. Okay, finally we have our chihuahuas. Not to pick on chihuahuas, but you know, they're chihuahuas. So, okay. We're gonna do the same process. We're gonna get the mean, M3. The mean here is 73.33. We're gonna subtract out the grand mean, which is 95. Okay, with me on this? And next we're gonna do that deviation, M3 minus GM. Let's take a look. It's gonna be a negative number, 73.33 minus 95. My calculator is saying that is negative 21.67. I'll do that 3 times. Okay, next I'm going to square that. M3 minus GM squared. 21.67 times 21.67. My calculator says that is 469.59. And look, that ended up being exactly what it was for the border collies, which I think makes sense because there was the same number of border collies as chihuahuas and the labs were exactly average. So I think that's kind of interesting. So that's 469.59. Write that out 3 times. Okay, and then SSB3 is the sum of that column, which we've actually already done up here, which is 1,408.77. I'll circle that. Okay, the reason that we got SSB1, SSB2, and SSB3, if we look at the formulas I put at the very beginning, is because big SSB is the sum of all the little SSBs. So, I hate to do it, but I'm going to erase this part of things over here. Okay, and what we have is big SSB equals the sum of the little SSBs, which is 1,408.77 plus 1,408.77 plus 0, which is 2,817.54. That's SSB, which is over here. Now remember, MSB, which goes into the F ratio, MSB equals big SSB divided by DFB. So MSB equals SSB divided by DFB, which is 2,817.54 divided by degrees of freedom between, which is the number of groups, which is 3 minus 1, which is 2, which is 1,408.77. kids, we're just about done with this particular step. F equals MSB divided by MSW. That equals 1,408.77 divided by
156.66.
156?
Yeah.
0.66. Thank you, Dana. Okay, so MSW, something we computed a while back, and there it is. It came back, 156.66. And if we do the math here, 1,408.77 divided by 156.66, and that equals 8.99. Step 4. Whew. Step 4 is a doozy. Sorry about that, kids. F obtained equals 8.99. Okay, so remember what F is. It's an index of how much between group variability there is relative to MSW, which is the amount of within group variability. And let me go back and put up our F distribution, which I erased before, but I'll put it back. Our F distribution looks about like this. Remember, the most expected point, sorry, that shouldn't be 0, that should be a 1. The most expected ratio in an F distribution, if there's no effect, is 1, meaning that MSB equals MSW. Our F critical, I believe it was 5.79.
Yeah.
Our F critical was 5.79. And just like with any other hypothesis test, we can think about this alpha region here. And our F obtained equals 8.99. It is in the rejection region. It is in the alpha region. F obtained is more extreme than its F critical. Therefore, we would reject the null hypothesis. Now, let's go all the way back to step 1 and think about what that means. Remember, the null hypothesis is that mu1 equals mu2 equals mu3, and the research hypothesis is simply not H0. Okay, therefore, think about what it means that we have rejected the null hypothesis. We've rejected the null hypothesis simply means we've rejected this assertion here. We have rejected the idea that the population mean for doggy IQs for border collies, labs, and chihuahuas are identical to one another. We have rejected that. However, we've only rejected that. We have not done more than that. Because of that, and this is the limitation of the analysis of variance, because of that, we don't really know a lot of information here. We don't know if this was driven by the fact that border collies are smarter than chihuahuas, border collies are smarter than labs, and so forth. We don't know what particular pattern drove this to be a significant effect. In real stats, and this is what I would consider in the more advanced category of things, in real stats we would need to do what are called follow-up tests. Okay, with follow-up tests, you follow up an analysis of variance to see what's driving it. One specific kind of follow-up test that you already know about, for instance, would be between group t-test. So like you could follow up your significant ANOVA with a between group t-test to see if border collies are significantly smarter than our chihuahuas, for example, or if border collies are significantly smarter than our labs, for an example. So a between groups t-test looks at two means to see if they're specifically different from each other, that is the kind of test that you would use to follow up on a significant analysis of variance. So ANOVA's cool, but it also is limited because when you reject the null hypothesis, the ANOVA itself doesn't tell you what means are significantly different from what other means. Okay, a final concept. I'm afraid I might have erased too much stuff.
I have it all written down.
You have it all written down, it's gonna be amazing. It's our associate producer Dana right there, by the way. Amazing associate producer. The final thing that we're gonna do is come up with an index of effect size for the analysis of variance. So hopefully you've seen this as a theme throughout the semester. Whenever we have a statistic, we have a way of doing a hypothesis test to see if we can say that the pattern found in the sample can be inferred to the broader population. And we will usually also do some kind of statistic that is an index of effect size, saying regardless of whether we're making an inference to the population, how big is our effect? The effect size index that we use, or at least one that we can use, as you'll see in more advanced stats, there's a lot of different effect size indices that follow or that can follow from ANOVA. My favorite happens to be R-square. Okay, so R-square simply is SSB over what's called SS total, where SS total, I'll put this as a little sidebar, equals SSB plus SSW. Okay, so for the F ratio, that takes the n's into account and the degrees of freedom into account. And it's looking at an index of between group variability over within group variability, but in a way with MSB and MSW that takes those n's into account. Remember, effect size tends to be free of the size of your n, and that's true of R square here. So this is why we're using the sum of the square deviation scores instead of the MSBs, because the MSBs take the n's into account. The SS, the sum of the square deviation scores, both between and within, do not take the n's into account. So this is more of a raw index of how big your effect size is. What I like about it is it's a percentage. So this is capital R square. It's different than lowercase r square we ran into a couple of chapters ago, even though it's similar in terms of its interpretation. R square can be interpreted as the percentage of variability between scores that is accounted for by between group variability. So scores vary from one another, like here's the lab scores. Any particular lab score, like here's one that's 90, that score is 90 for two reasons, or in ANOVA speak, we say there are two sources of why that score is what that is. One source has to do with what we call within group variability. So the labs vary from one another. Not every lab is identical. And so there's within group variability. And another source of why that score is 90 in this particular case is because it's a lab. And the average for labs, on average, is different from what it is for Chihuahuas and for Border Collies. So there's two sources. And what the R square is telling you is what percentage of that variability is due to the between group variability relative to the total amount of variability, which is just the between group variability plus the within group variability. So Dana, if you could remind me, SSB equals?
2,817.54.
Okay, so big SSB was 2,817.54, and we're going to divide this by that same number, 2,817.54, plus the within group variability, which was what? SSW.
Yeah, 783.29.
783.29.
Yeah.
Okay. And so time to get out the calculator, kids. Okay, so that equals 2,817.54 divided by 3,600.83. And let's see what my calculator is going to give me on that. My calculator is saying 78%.
Yeah.
Okay, so R square in this particular case is either you could say it as 0.78 or you could say 78%. The way that you would write that, the way that you would explain that to someone is you would say that 78% of all the variability in IQ scores for the dogs was accounted for by what breed the dog was. The between group variability accounted for 78% of how smart those dogs were. I hope you've enjoyed the stats class, kids. I hope you can see the relevance to your everyday life and to real life situations. And I hope and trust that you continue to advance your statistics education. This has been Stats with Glenn.